Hello, so today we are going to do this problem, minimum falling path sum, which is part of Leetcode daily today. So basically we have a matrix, an n by n matrix, and we want the minimum sum of any of the falling paths through the matrix. And what do they mean by falling path here? Basically is that it starts at any element from the first row, so any of these. And then you have only the 3 possible moves each time. You could, for example, from here, you could either move to the next row directly below, or you could move diagonally left or right. Okay, so for example, for one here, you could move directly below to the next row, or left diagonal or right diagonal. And then you could do that from here as well, but from this two, you can only do this or this because there is no left diagonal position. And basically that's the idea here. Now the goal is the minimum sum that we can do from the first row to the last row. It doesn't matter from which position into which position, it doesn't matter. But we are only allowed to do the down move or left and right. And we want to return the minimum sum. Okay, so for example, the first example here, there are 2 possibilities to get the minimum sum, which is the same value 13. You could start from 1, go down to 5, that's 6, go to 7, that's 13. Or you could go right diagonal to 4 and then left diagonal to 8, and that's 13 as well. And this is the minimum you can do. If you try other variations, they are all going to be bigger. So that's the idea here. The bounds are not too big, up to 100 rows and 100 columns. So oven squared solution should be fine. Yeah, let's see how we can tackle it. Okay, so let's see how we can tackle it. So the first thing to think about is from each state, we only have 3 possible positions, right? From ij position, we can only either go to left diagonal, so that's the next row left diagonal, so I plus 1j, or we can go to the right down, so basically we could either go here like this, and this would be I in this position j, so this is j minus 1, and then this is I plus 1, okay? And so this is I plus 1, j minus 1. Or we can go directly down, so we stay at the same column, but go to the next row, so I plus 1j, or we could go right, and so that's j going I plus 1, j plus 1, and the next row I plus 1, so this is like this. And then of course, let me just put that down this, so 3. And so that's not many states, so maybe we can just actually just do simple recursion and just go through, for each position, go through these 3, and then just pick the minimum. Right? Each time pick the minimum that we get from, and then each one will go and go down as well, all the way to the bottom until it reaches the bottom row. So what do I mean by this? So what will happen, for example, is we can start with all of these positions. Okay, so we start with 2, 1, and 3. Each of them start its own recursive call, and then 2 will go tries this and this. And then these will recurse on, this one will recurse on this and this. Okay, so these 2, once it recurs, it will pick 7. It will bubble 7 up. So it will bubble 7 up here. And so which one to pick? 7 plus, so this one will say, okay, I have 7 plus 6. That's 7 plus 6, that's 13. Okay, so this one has 13 now. And this one, 5, will try this, and of course we'll pick 7 because that's the smallest, and so 5, 7, that's 12. And so 2 will say, well, should I pick 13 or 12? Well, better to pick 13, so 2 will pick 13 and it will have 14 here. Okay, 1 will do something similar, it will go to 5, 6, and 4. Each of them will go down. Okay, and 5 will find that the smallest one is 7, right? So it will add it to itself, that's 12, and so it will bubble 12 up to here, and now we have 13 here. We'll do same thing for 3. 3 will try this, and each of them will try what it can. So 5 will try this, which we already tried. It gets 12. 4 will try 9 and 8. It will pick 8, and so 8 and 4, that would be 12. And so 3 can pick either this 12 or this 12. It doesn't matter really. We have 15. And then we'll pick the minimum among these 3. And the minimum is actually this 13, right? So that's the idea. We can just recurse on all the choices, pick the minimum, bubble it up to the caller, and keep doing that until we get to the first row. And then the first row chooses the minimum, right? So that's our approach here. So let's just call recurse on 2 positions. And then what we need to do is do our base case, which is basically reaching the last row. It doesn't matter which column. If we reach the last row, we just want to bubble back and return 0. Why return 0? Because you will see I will add, for each recursive call, I will add the value before going down, okay? And so here we can just do, if we reach the last row, return 0. This is our base case. Now we can do our recursive call. Well, we said these are the states we have. So for the next j position, we can either do j minus 1, j, or j plus 1. So j minus 1, j, or j plus 1. And we will go down only if it's within bounds, of course, just to not go in something that will get us indexed out of bound. And we need to recurse on the next row, right, I plus 1, and then one of these j's, and so that would be this nj. Okay. Of course, we need to define n as the length of the matrix. I will call this a just because it's easier to write. Now, here we want to take the minimum amount. Remember, when we were doing this, each time we were here, for example, it took the minimum out of the 3 choices, and these in turn also took the minimum out of their choices. And so each time we want to take the minimum. Okay, so we want to take the min of this with the previous one, and so we'll just store the previous one in a variable best, and we will initialize it to the highest value possible, so that the first choice gets assigned, and then we compare it with the next one. Okay, so we'll just pick here, just pick a very high number, so infinity here. And then at the end, what do we want to return? Well, we want to return best, but we shouldn't forget to add the value itself. Like here, when we bubbled 7 up to 5, 7 added itself, and we ended up with 12. When we bubbled 12 up to 1, it added itself, and we had 13. And so that's what we should do here. We should add the value itself. So that's I plus 1 and j. That's the value that we want to add, and then recurse for the next rows. Okay, and that's pretty much it for this. But remember, we want to try it for all the rows here, for all the values in the first row, because we don't know which one would be the minimum. And so here we can just say return the min for all of them. So of course we want to recur for row 0, right? But j, we want to try all of them. So let's call it for j in all of them, so range of n. But we also, like we did here, we want to add the value itself. So for example, here we add 1, and here we add 2 for the recursive function that went into the next positions for 2. Right? And so here we want to add a0j plus this, and then we pick the minimum. Of course, you can do something maybe clever. For example, you maybe do recur for -1, right? For all of these positions, but that doesn't really simplify things by a lot. Okay, so this should be it. We can run this, make sure it's good. Okay, looks good. Let's submit. You can, of course, as well cache this in case the same I and j gets called. And so we'll do that here, because we probably may end up with some recursive functions, right? Because let's say position, so for example, if you look here, position 2 needed to call 6 and 5. position 5 needed to also call 5 and 6, right? So you can already see there is repetition there. So we need to cache this. Let's just do a simple cache using Python annotation. You can use a hash map if you want to. And this gets accepted, okay? So this is sort of recursive, or it's also called dynamic programming with memoization. We can try to do like some sort of bottom-up dynamic programming, which is basically using just for loop, and it's really easy to do once you have this format. It's really easy to sort of convert it to it. So let's do it. So we need an array to store our basically the results that we have. So it needs to be the same length, same number of rows and columns as the matrix, right? Like this. But we also need the first row. Like here we are populating the first row, you see it already. We need to do the same thing here, where the first row is just the first row of the matrix. Let's see. So we do that first, and then here you can see already, we do this in order. We start from 0, we go to 1, we go to 2, all the way to the bottom. So that's exactly what we can do here. But here we already filled row 0, so we can start from 1. And for J, for this specific case, we want to try all of them, because we are not going to do it like individually. We will try for each ij. We'll need to check. So basically, what do I mean by this? For each ij here, it's a little bit of the inverse. What is the result we get for ij? Well, we get the result from the previous, we get to this ij from the previous row, I minus 1. And left, maybe we came from the right diagonal, right? So maybe we were here, maybe this is 5, and we came from here. Now, if we came from this 2, then it's actually I minus 1, j minus 1. Or maybe we came from 1. Okay, if we came from 1, then that's just ij, I minus 1j. Or maybe we came from 3, which is I plus 1, I plus 1, I minus 1, because it's the previous row, and j plus 1, right? Because this is 1 and this is 2, okay? And so this is I minus 1, j plus 1, okay? So these are the 3 previous states that we can use. And so here, dp of ij is going to be the min of these 3. But remember, we also need to add the value itself. We should not forget that. And so here, first, let's just add the value itself, which is I. Of course, I forgot to initialize n, which is just the length of a. And so this is ij plus the min of these 3. Okay, so the min of these 3. Now I just need to make this actually call the previous states. Now this is fine. We are doing this minus 1 instead of the plus 1, because when we are, let's say, at I2, row 2, we already pre-calculated for row 1, but not for row 3 yet, only for row 1. So we have to use the previous state that we already computed. And so that's why we are doing this here. And so this is I minus 1, j, and this is dp of I minus 1, j plus 1, okay? So we take the min out of these 3. And what else? So we take the min out of all these 3. We of course need to handle the case where this is maybe out of bound. The simplest way to handle it is just to max with 0. So let's say, for example, if we were at maybe this position, right? We can't do left. And so if we max with 0, we'll just take 2, which would be the same as taking j, right? Which would be the same as taking this one. This one would be the same as taking this one. So that's fine, because the min of the same values is just the same value, right? So that's why the max here. And similarly, for j plus 1, we can just take the min of n minus 1 and j plus 1, okay? Because actually, the same reasoning here. If we are, let's say, maybe here, we can't go here, but since we are doing the min for n minus 1, we'll just take this one twice. and do the min of it twice with this one, which is same as doing it once, right? So this should work. And now what do we want to return? Now remember, here we did it for, we did the min for all of them. So that's exactly what we'll do here. We'll do the sums until the last row. We'll add 9, 8, and 7 for each corresponding position. And so we can just take the min of the last row in our DP array here. And so we could just return the min for the last one. Okay, and that should be it. That should give us the same result. So we can just remove this and run this. And looks like it's good. Let's submit. And this gets accepted, okay? Now, this here can be simplified a little bit, because you can see here we are just for each position, we are just adding to A itself. So here we have O then by N space. So we can actually get rid of that. So to do that, we can just, instead of creating a DP array, we can actually just reuse the exact one. So this here, we can just take ij, because we were already adding it, so may as well just add to it, okay? And we don't need to initialize to A0 because we already have A0 at the first position of A, right? And here, this is just going to be AI minus 1 because we would have already assigned to that position. And same thing here, and this is same thing, right? So we'll just accumulate in place. Since we were already adding every cell position, every cell value, we can just add on top of that cell value, right? So if we run this and submit, it does get accepted, okay? So this makes it O1 by N time, so O1 squared time, but O1 space. Of course, this is only if you don't need still access to the content of A. Yeah, so that's pretty much it for this problem. Thanks for watching and see you on the next one. Bye.